A lot of quantities are built in stages. The temperature of a room depends on the setting of a dial, and the setting of the dial depends on the time of day. One thing feeds the next. So here is the question. When the first thing changes a little, how fast does the thing at the end of the chain change? Each stage has its own rate of change. The first rate tells you how the middle responds to the input, and the second tells you how the output responds to the middle.
So do I add those two rates or multiply them or something else?
That question is the chain rule, and the answer is cleaner than you might guess. Before we combine two rates, look at just one. Back when we met the derivative, we saw it as a local stretch factor. Zoom in on a smooth curve, and it looks like a straight line, so near a point the function just multiplies a tiny input change by one number. That number is the derivative. So picture a single stage as one gear. A small change goes in, and a change comes out, stretched by the gear's ratio. For a function, that ratio is its derivative at the point you are sitting on. One stage, one rate. Here are 3 dials in a row. Turn the first and it drives the second. Turn the second and it drives the third. The first dial is our input, the symbol X. The middle dial is what X produces along the way, and the last dial is the final output.
So a change in the first one has to travel all the way through to the last.
Exactly, so give that first dial a small nudge. The question is how big a change comes out the far end, once that nudge has passed through both couplings. At the first coupling, the nudge is scaled by the first rate. Here that rate is 2, so a small turn going in becomes twice as much turn in the middle. At the second coupling it is scaled again, this time by 3. So that already doubled turn becomes 6 times the original by the time it reaches the output.
So why do the two rates multiply and not add?
Because the change passes through the couplings in series, one after the other, not side by side. The first stretches it, and then the second stretches what is already stretched. 2 and then 3 gives 6. The rates multiply. That is the chain rule. There is one honest catch with the gear picture. Real rates are not fixed like gear teeth. The stretch factor changes depending on where you are along the curve. So the outer stage does not have a single ratio. It has a different ratio at every point.
Then which point do I use for the outer rate?
You read it at the inner stage's output. The input is the symbol X, but the outer stage never sees X. It sees what the inner stage produced, g of X. So you evaluate the outer rate right there, at g of X, and never at X itself. That is the one place people slip. Here is the classic example, an inflating balloon. Its volume depends on its radius, and its radius depends on time. 2 stages again. How fast the volume grows per second is how fast it grows per unit of radius, times how fast the radius grows per second. Now watch the 2 rates. The inner one, radius per second, is roughly steady, because you are pumping at a constant rate. But the outer one, volume per unit of radius, is the surface area, and the surface area plainly grows as the balloon swells. There is your changing gear, made visible. The same small push on the radius moves far more volume when the balloon is already big. And that is the chain rule. Rates in series multiply, each one read where its stage actually operates. Run this same rule backward through the layers of a neural network, and it is exactly backpropagation. Run it backward on an integral, and it undoes a composition, the reverse chain rule we will meet with the fundamental theorem. Rates that nest multiply.